Welcome to this explainer on system design. Every time a popular website loads flawlessly during a massive traffic spike, there is a hidden architectural dance happening right behind the scenes to make that possible. Let's dive right in. One of the absolute most confusing topics for anyone exploring system design is understanding the exact differences between three very specific architectural components that constantly get mixed up in casual conversation. At first glance, a reverse proxy, a load balancer, and an API gateway seem to do the exact same thing. They all sit firmly between the client and the application, receiving requests and forwarding them somewhere else. So could one of them just do the whole shebang? Well, this raises a fascinating question about why all three actually exist. Mixing these tools up is not just a simple vocabulary error. Deploying the wrong component can lead to massive network bottlenecks, wasted server budgets, or even catastrophic security flaws in a production environment. The answer really lies in the highly specific problems each one is engineered to solve. Here is the agenda for this explainer. First, the system design confusion. Second, reverse proxy, the front desk. Third, load balancer, distributing traffic. Fourth, API gateway, the check-in. And finally, how they work together.
Section 1. The system design confusion.
Let's begin by looking at the specific challenges that arise as an application scales up over time. When developers build an application, say a brand new e-commerce platform, that suddenly goes viral, they encounter some unique and pretty terrifying problems. Just imagine a single monolithic server struggling to keep up with a viral product launch. Users are constantly browsing products, logging in, attempting to check out, and placing orders all at the exact same time. Every single action sends a request to the back end. As the application expands to handle this chaos, distinct growing pains emerge. There is a sudden need to protect fragile back-end servers from malicious actors, a critical need to distribute massive amounts of traffic so the whole system doesn't melt down, and a need to manage incredibly complex APIs. Each of these massive challenges requires a highly dedicated, specialized solution.
Section 2. Reverse proxy, the front desk.
The very first major challenge a growing application faces is keeping its infrastructure entirely secure. A reverse proxy acts as a protective shield that sits directly in front of back-end servers. Its primary job? Ensuring that external users never, ever communicate directly with the internal servers. By masking the internal IP addresses, malicious actors absolutely cannot target the database or core servers directly to launch a targeted DDoS attack. Instead, every single request first reaches the reverse proxy, which then safely forwards it to the appropriate back-end server and ultimately returns the response. Think of it exactly like the front desk of an exclusive apartment building. Imagine someone trying to wander directly into a stranger's living room. That would be chaotic and highly dangerous. That is exactly what a reverse proxy prevents in a network. Visitors do not just walk directly to an apartment door. They only know the building's main entrance. They go to the front desk, which then decides exactly where to send them. Visitors have no idea how many apartments are inside, where they are, or how they are laid out. A reverse proxy works the exact same way. Users only ever know the public address, keeping the entire backend completely hidden and perfectly secure.
But wait, beyond just forwarding requests, a reverse proxy is incredibly versatile and handles some serious heavy lifting. It can cache responses to dramatically speed up load times for frequently requested data, and it can seamlessly compress data to save precious bandwidth. Here is a surprising fact. Terminating HTTPS connections to ensure secure communication actually requires immense computational power. By offloading SSL and HTTPS termination to the reverse proxy, back-end servers are saved from an immense amount of processing strain, allowing them to focus purely on delivering the application itself.
In real-world applications, developers frequently rely on powerful, established tools to perform these demanding tasks. Some of the industry's most popular reverse proxies include NGX, Apache, and Traefik. To put that skill into perspective, NGX is so ubiquitous and incredibly efficient that it currently powers a massive percentage of the entire internet's active websites, processing incoming requests safely and silently in the background every single second.
Section 3. Load balancer, distributing traffic. As popularity surges, a single hidden server will eventually become overwhelmed, introducing a completely new issue. When one server is no longer enough to handle thousands of users, developers deploy multiple identical servers. But when a new request arrives, which server should handle it? Well, a load balancer steps in to solve this by receiving incoming requests and intelligently distributing them across multiple healthy servers, completely preventing any single server from crashing. The load balancer actually acts like a network medic.
It performs continuous health checks, pinging servers constantly to ensure they are alive and responsive before sending any traffic their way. This is exactly like a busy supermarket on a Sunday afternoon. Instead of sending every single customer to the first exhausted cashier, which would result in an agonizingly long line and a very stressed employee, the supermarket opens 4 checkout counters. Customers are naturally distributed across all available counters so that everyone gets served much faster and no single cashier is overwhelmed. This greatly improves overall system availability. If one server goes down, perhaps due to a hardware failure, traffic is automatically and instantly redirected to the remaining healthy servers. Knowing which load balancer to deploy, whether utilizing AWS Elastic Load Balancer in the cloud, Azure Load Balancer, or HA Proxy for an on-premise setup, is a fundamental decision for ensuring high availability. It guarantees the application stays online even when individual pieces of hardware inevitably fail. Section 4, API Gateway, the check-in. Modern applications often break down into multiple microservices, creating vast complexity. Instead of one giant monolithic backend, imagine an application split into a user service, a product service, an order service, and a payment service. If a client application on a smartphone tried to securely log into all 4 of these different services simultaneously without a central gateway, the network traffic and security handshakes would be pure chaos. Clients shouldn't have to memorize different URLs or handle complex authentication for every individual service separately. An API gateway solves this by providing a single, unified entry point that rigorously manages and routes all of these fragmented requests. Consider an international airport check-in counter. Before boarding a flight, a passenger first goes to this central desk. The staff acts as a strict gatekeeper. They verify the passenger's passport, check the ticket, confirm baggage weight, and only then direct them to the correct boarding gate. The check-in counter doesn't just point the way. It acts as a strict enforcer, ensuring all security and business requirements are completely met before allowing anyone to continue into the terminal. Just like that rigorous airport counter, API gateways like Kong, AWS API Gateway, Azure API Management, and APG perform critical checks. They authenticate users and validate permissions. They also apply rate limits. Without rate limiting, a sudden spike in traffic or a malicious bot attack could literally bankrupt a company's server resources in minutes by processing infinite bogus requests. The gateway stops that right at the door, applying limits and then safely forwarding the legitimate requests to the appropriate microservice. Section 5. How they work together. We have looked at the isolated roles, but the magic happens when zooming out. The crucial point here is that these 3 tools absolutely do not replace one another. Comparing them side by side makes it extremely clear that each solves a highly specific problem. The reverse proxy acts as the apartment front desk to hide infrastructure. The load balancer acts as supermarket checkouts to distribute traffic. And the API gateway acts as the airport check-in to uniquely manage the API entry point.
In modern system design, these components are fully intended to be layered together. A load balancer alone doesn't secure endpoints, and a reverse proxy alone won't manage microservice routing logic. It is the combination of these puzzle pieces that collaborate seamlessly to build a deeply robust, highly scalable, and exceptionally secure digital environment.
Let's see how this builds into a complete journey by tracing the exact lifecycle of one specific request. Imagine someone tapping Buy Now on a smartphone. First, that request hits the reverse proxy shield, keeping the internal network completely hidden from the open internet. Then, that request gets passed to the load balancer, which instantly calculates the healthiest, least crowded pathway. Next, it passes through the API gateway, which strictly validates the authentication token and checks rate limits. Finally, having passed every single test, it reaches the exact right order microservice to complete the purchase, a seamless, secure relay race executed in mere milliseconds. Understanding these foundational components is essential for grasping how our modern digital landscape actually operates behind the scenes. But as systems grow ever more complex, handling millions of requests per second, one has to wonder, as applications continue to evolve, what architectural innovation will become the next new standard to manage the chaos tomorrow? Thank you everyone for tuning in to explore this topic today. Keep questioning the systems that power the digital world.